Wait, we have some function a to b. Then we also have, so now we want to say that, what's injective 2? Let's do this. There exists G type B to A such that, oh wait, I think this is wrong. This should be F after G. Okay, so let's think about this. So let's do this way. So injectivity implies left. Okay, so actually, how do I rewrite or unpack the definition? I think, yeah, I think I can just do rewrite injective. Okay, there we go. FA1, FA2, and then can I give it like A1, A2? No. So what about our cases? Injective with fuck. Does that work? Oh wait, first we need to do okay. All right, so now we have this, and we just need to imply. So let's just do intros A1, A2. That doesn't work. It's not intros, it's something else. It's like is it not? Maybe it's our cases. Well, yeah, first off, intro finj. But then I want to say our cases but then our cases takes a hypothesis, so let's do finj at ay ay ay. Can I do at something? Intros at. Let's just ask how to um, replace universal quantifiers in a hypothesis in tactic theorem with, I think it's called with specific named but arbitrary. Oh, really? That's nice. That's the one that I want. We didn't do that to specialize. A1, A2, Finch. What? This should work, but this isn't working. Specialize requires a term. Yeah, should be right. Why is it giving me trouble? Much better. Holy cow. That's so much better. Intro A1, A2. This doesn't work either. I don't know what they're talking about. A correct proof of injective if and only if there exists a left inverse. Wait, let me just try the exact. What is it? Function not injective. Does that work? It made that up. Actually, I want to try this. All right, so this is kind of the clean way to do it. Is instead of, well, all right, yeah, let's look through function. And I actually want to, I guess I want to do an import. Import mathlib.data.function. Is this one file? Data.function. Okay, cool. Oh. Why did it error? No such file. I don't get this, dude. It's like, this is clearly here. Wait, I don't even know. Why can't I import this? Are you not allowed to import this? Mathlib.data.function. Oh, because I don't think it's in Mathlib. I think it's just import data.function. No. Import function? Um, I say we don't even need to do this. I think there's no point. Doesn't exist though. So this is. I see. What is this symbol? Strict implicit binder. Implicit binders, strict implicit binder. In contrast to implicit binders, strict implicit binders do not automatically insert an underscore placeholder until at least one subsequent explicit parameter is specified. I have no idea what that means. Example, if H is of type for all X of type A, X in S implies PX. And HS was of type Y's in S. And H by itself elaborates to itself without inserting underscore. Okay, that means nothing to me, man. Why don't they use the exists? Is it the same? Has left inverse dot injective. Is there an injective dot has? If F is of type A to B, G is of type B to A, H is of type left inverse. Why does left inverse take two? Okay. All right, so you need to actually have it. That makes sense. All right, so then this states that G is a left inverse of F. Okay, so this is exactly kind of what. All right, all right. Um, do they have the not equal? Oh, this is the contra. Wait, what is this? What is MT? Oh, MT. Oh, really? Dude, I love how freaking compact these proofs are. Like MT is like what does this even stand for? a modus something. It's like a contrapositive of modus ponens. If A implies B and not B, then not A. That's crazy, bro. That is really, really crazy. Okay, so wait. All right. I think I need to come up with the algorithm for how to like learn how to do this. So the first thing we want to do is we want to just we're gonna comment this out. We're gonna rewrite it again because I just need the repetition. Theorem, injective, if and only if has left or has left in. We'll just call it the same thing. And we have a function of type a to b, and we want to show that in function dot injective f, if and only if function dot has left inverse f. Okay, so I think we fully set up the thing. And now we want to find first the exact theorem that does the if and only if. So I'm going to try to find some sort of if and only if. So there's that. That's kind of weird. You would think that there would be that theorem. So let's just do the constructor, and then we're going to use the fact that left inverse. So first off, has left inverse. Okay. Where are we at here? So constructor. Okay, C dot. Wait, what's going on? Constructor. Okay. Now we have the NPR. Injective implies has left inverse. Left inverse. So wait, first can we do sorry here, and then we can do. So now we want to exact function dot left inverse dot injective, has left inverse dot injective. So this is like, okay. Ugh, I hate this thing. What? I don't like that we're not allowed to do this anymore. I feel like I just want to leave it as is because it's like, why did you guys do that to me? Okay, but then this one, the proof that injectivity implies is that there is a left inverse. Okay. So this is in like lean source code. So let's actually go to the lean source, lean 4 GitHub. Okay, and this is going to be in source. Is it lean? I guess it lowercase state. Lean data functions. Wait, what? Wait, where is it? Oh, wait, what? Lean. Oh, init. Lean init data, not lean data. Lean init. What? This is old? Did they move stuff around? Can I just look up function.lean? Source init. I guess something happened there. But this is definitely it. Um, I can only find half of it. But so I think that this is going to be the best plan is this is like the math lib proof. So we kind of get more, we do the simplest thing and then we can get finer and finer grained. But the first thing is just prove the exact same thing as MathLib, just to use the fact that, just to use the facts that they already have in there. Wait, if wait, why is that not in general true? Oh, so we need to say that it's non-empty. Why are they using the square brackets? So we have this. Type class arguments. I don't know if it's the same for this one, but we need to do it for this one too. Yeah, because the problem is if A is empty, then there's no function G. Okay. So first off, let's look at the proof of this. If it has a left inverse, then F is injective. And the proof is defined by a function h2 um FAE, what the frick? Faquif. Oh, FA equal FB. I get it. FA equal FB. The problem with these proofs is that they're so... Oh, actually, it does change. That's nice. Okay, so we have G, we have F, we have the hypothesis H, and then we have A and B, which are type inferred to be type alpha, and then we have FA equals FB. Um, wow, unraveling these definitions is psycho. Okay, wait. So let me just, without getting so into this insane mess. I mean, is there any value to these proofs being like so dense? I have no idea. But okay, let me just try to go. Um, let's do one, and then let's do like this way. So if it has if as left in, then G circ gaf equals I don A. Okay, what that means is that if we have A1 and A2 in A, then GF of A1 is equal to A1 and GF of A2 is equal to A2. So A1 equals A2 on okay, so GF of A1 equals GF of A2 only if A1 equals A2. Definition of injective. That's my understanding, right? Like, is that right? Or yeah, I did flip it. You're right. Yeah, it's right. Ah, yeah. Okay, cool. Okay, so wait. We're gonna copy this again, and instead of this, first we are going to intro HL. And then what I want to do is get the G. So how do I get G from has left inverse? By eliminating. Obtain GHG defined as H. Obtain. The obtain tactic is a combination of have and are cases. I want to name this. I don't want this thing like that. So what is it saying? It's saying obtain G HG defined as HL. Wait, what is it? Well, okay, wait. First, we need to say intro HL. That's the first thing. Then we need to say define as HL. Oh, here we go. So now we have the G, and then we have the theorem that says that G is the left inverse. Okay. So now if let's see, how do I think I should be able to say rewrite function dot left inverse at HG. Okay, cool. Oh, I think what I do is you say, okay, I'm getting the hang of this. You say have, uh, uh, oh, wait, but, okay, wait, instead of doing this, rewrite, RW rewrites in place. You have to use let. Oh, but I could just do let. Have, but I don't want to like write it out. Oh, you could do that too. Where's the let? What if I say let HG? No, you can't really do that. So okay, I say that this is probably the simplest way to do it. Is you just do HG and you say rewrite H function dot left inverse at HG. So now we have the old one and the new one, just like. And then I don't know what this is about. Wait, actually, this doesn't seem right. I think what we want is we want have here. So now HG is the definition of. So can I do now if I have something like this? What is this whole? Non-computer def some left in H has left in B to A defined as classical dot choose H. What? Okay, so what do we do? Okay, wait. So here's what I want to do. I want to do rewrite function.injective. The problem is that we didn't get to so in my notes here, like this got rid of the existential, right? Or the exists. I forget. How do we get rid of exists? If for all is in a hypothesis, and then this is refine. R intro exists x p x implies q. You now have x and what is hx? Hx is p of x. Oh, that's actually nice. Okay. So where are we at? Oh, wait, this is not the right one. But so for all, we want to do intro, but I think, oh no, we did get it. Oh, frick yeah, bro. Now we want to show that, um, so I think what we want to do is we want to combine this and this, right? Because both of, well, actually, for all, so type A. So we know that FA1 equals FA2. So if we replace FA1 with this in here, we're going to get A1. And if we do this thing too, okay, wait. Here's all I want to do right now is I want to apply now I want to rewrite okay, wait. Kongrarg calc. What the heck is this Cyrillic? What is this? What? Accidental Cyrillic? What the, what the hell? That was weird. That was really weird. Oh, wait. Wait, so if I did um I forgot about the calc tactic. All right, I'm down to try calc. And what do? Define by apply. Is apply a tactic? Yeah, apply is a tactic. Oh, we gotta go slower. Okay, where are we at here? I just want to show. Oh, wait, here's what I can do. Have foo of type A1 is equal to GFA1. Well, I don't even want to do that. I just want to say GF of A1. Then I'm just going to do by exact HG, right? And then like this. Type mismatch. HGA1 has type. Oh, bro. Can I just do .sim? All right, cool. So now we have foo. All right. How does this .sim thing work? Like, how does it know that? How does that work, man? So eq must be like the root node of that expression. And so then it like looks and sees like, okay, we can do sim. All right, so we have A1 is equal to GF of A1. And but then what if I did rewrite HF at foo? Nice. Okay, now I want to rewrite the right-hand side of that thing. Can I do apply at? Can I do that? Bro, come on, give me the doc string, dude. What the hell? Now I want to write. Can I write apply HG at foo? Can I do that? Cannot failed to find. Uh, yeah. What about this? Could I change that to a rewrite? Rewrite HG at foo. I think I have to put this in a list. Oh, sick. Nice. That's the proof. And then now we just need to do the harder one. This is actually the easy one. Or HG. What is the definition of constructor? If the main goal's target type is an inductive type, constructor solves it with the first matching constructor or else fails. That is super vague. So somehow if and only if is some sort of inductive type. Let's look at the book. How did the book do it again? I prefer this contrapositive definition personally. Because it's easier to think about if you have two elements in the, what's it called? The domain. Then because G can only send, like, how could G, like, suppose that F A prime and F double A double prime were different, then or we're the same, then there's no way that G of that could be different. But it's clearly different because of the fact that it's yeah. Okay. All right, let's do the other part of the proof. So this one seems harder actually. Okay, so first off, intro, hinge. So we know that A is okay, and then what do I want to do? I want to obtain the or no, we can't really do that. Okay, wait. Let me just write it out. So since um that's better. Let's do that. partial left inverse. So then, since F is not guaranteed to be surjective, we choose an arbitrary element of A to send a B backslash MF to. But I don't know how to do this one. The fiber of Y. Define G of B to be the A such that F of A equals B if such an A exists. If no preimage exists, send it to some arbitrary default element of A. This is where non-empty A is used. Okay, classical What does that mean? What? Runs tactics in a scope where classical dot proposition decidable is a low priority local instance. That's some advanced stuff. I don't know what that is. I really don't know what that is. Yo, it's freaking Riley, dude. What's up, Riley? I didn't see that you were there. I'm chilling. I'm I'm chilling. So wait, why is this I don't think that that's actually a thing. I think it's fine. I don't know what's up with the classical error. Um Let G be a function from B to A defined by fun B to what is dite? Dependent if then else? I don't know if that's a real thing. Oh, so I should be able to just use injective like that now. Oh, that's nice. Okay. That's a lot nicer. Okay, so they're saying let G of type B to A be defined as fun B goes to what is dite? I guess dite is real. Decidable if then else. Or wait, no, not decidable. Dependent if then else. So if there exists an A such that f of A equals B, wait, don't I'm gonna switch these? Auto clicker time. Nice, bro. So wait, what is this? Explain this. What is this? If H, oh, does dite bring up a H? Oh. Oh, dite gives you the H, I think. Okay. Given an input B, we produce an element of A. Dite. If H is a term of type exists A type A such that FA equals B, then you get access to H. You get access to not H. So then choose H. So in the true branch, if the condition is true, you have H of type this. Choose one witness from that existence proof. Okay. So, okay, so wait, hold on. I want to do a theorem has a. So let's say that we have a theorem H of type exists A of type A, and that's like the whole thing. And we want to produce an A. What's wrong with this? Unexpected token. There exists an A. A is of type A. Is that a, how do I do this? Oh, is of type. Oh, yeah. We're trying to produce a term of type A. Yeah, yeah. So, but it's still not right. Is this A? H is. I don't think there's anything else. I don't know why it's erroring at me. It's not a proposition. What did I do wrong? What did I do wrong, Riley? Okay. Okay, wait. I actually want to do this theorem one. So, actually, I want to say let or have foo of type A defined by classical.choose H, right? And now I can just exact foo. I wonder why. I wonder why that thing works. The syntax is. I still gotta get my head around that. That's kind of strange. All right, so what do we do here? Okay, in the true branch you have this, and classical.choose picks an A of type A. So this branch returns an A. Okay, that kind of makes sense. All right, the false branch. If the condition is false, you have no preimage, but an HNE. What is HNE? Oh, cool. Wait, okay, hold on. Can I try the other way where I have, or let's say example, from non-empty, and then all we have, I don't want these sorts. I don't like these things. And all we have is that HNE type non-empty A. And we want to produce a thing, and then all I want to do is exact classical dot choose HNE. Can I do that? Can I what if I do rewrite non-empty? Can I do that? Prop where oh wait. That's what exactly what I oh wait, did I do I said choose instead of choice? Oh. Choose choice. Okay. All right. There we go. And this is example showing how to use a element from non-empty type via choice, not choose. Failed for the type binder. Can I do this? Yeah. From oh because oh lol. And then why does this fail? Consider marking it as non-computable. What? What if I just get rid of this? Can it just infer that? There's no format document. I don't know exactly what the deal is there, but there's something there. All right, so back to where we were at. We are trying to define this function, and this function's first going to take a prop, and the property is going to be that exists a type A. We should be able to infer that such that f of A equals B. Okay, and then the second thing is, so that's the first argument to the function, right? And we don't do this, we just do this. Okay, then we do fun h2. So in this case, do we have h? There's something weird going on. But yeah, let's do classic gold dot choose h. So we get this hypothesis. But how? I'm not seeing it though. Okay, so we have that now, right? We're good. We have G. Fun B, if H is of type exists A such that FA, then classical to choose H from that exists. That's right. And then otherwise take a choice from the fact that it's non-empty. Okay, then now all we need to show is basically that for all, okay, so now at this stage, now we just need to because the definition of left inverse yeah, so because it's a total function, we do need an assignment for it. They just have to exist. Okay. All right, so let's just show where I'm at. Yeah, what if I Ah, okay. So any function type is total by just the rules. You gotta follow the rules. Is none like a keyword? Is that like just part of the deal? It's a function that takes a. Oh. Huh. All right, that's cool. So where are we at right now? We need to. Okay, wait. How are we gonna do this now? I think I'm only gonna do this one. I don't think I'm gonna do the other one. This one was so involved. Maybe I'll do like this one, the other one tomorrow or something. Because now we need to show let. So this thing, we were able to construct G of type B to A. So we already have the guarantee that G is total. Then, okay, makes sense. So now all we need to do is okay, refine G. Oh, that's actually smart. That's what I'm gonna do from now on. Wait, did it? Wait, I feel like I had it though. Oh, that's so cool. Hmm. I'm not really sure what the deal is there. But now, Have hx exists a prime if a prime equals. Let's just see if this works. What is up with this? Oh, it worked. So let's walk through it just to see. Okay, now we have a term of type exists in A, so the images are equal. Unfold G, FA, and reduce the dite if using hex. So have okay, so what are we doing? We're applying injectivity, so after that's so messy. What does this even mean? A simp G. Do we even need this? Oh, see, there's so much weird stuff with this. Like the cursor, it's like, why does it say no goals removed? But then I don't really get that. What if I just do simp G? Like alone. This is a very strange proof. But you know what? It clearly satisfies the left inverse property. So should we just move on? I don't know. I don't feel good about that. Because the main problem with this part of the proof is this function and showing the left inverse. So we refine this. So now we try to use Now we're trying to prove that G is the left inverse. Okay. Now what I would want to do, okay, so intro A. So now what we want to show is FA is of type B. If we used this term in B, it's guaranteed that we'll be able to choose A from this. But I don't get this whole thing here. Have hex will exist at A prime if A prime is equal to FA. Okay, defined by A reffle. Okay, I don't really get that. Unfold G at FA and reduce the if statement using hex. After simplification, the goal becomes classical that choose hex equals A. So we have blorp equals choose hex equals A. Why does this rewrite the? Or no, it's because we're in here. So now we're trying to choose a sub goal. And we're trying to prove that choose hex is equal to A. Apply injectivity. Simp A. Will simplify the goal and the type of E using rules. So what happens here? Okay, so here we showed that choosing an element A prime So now since B is equal to f of A, if we put f of A in here, then we should be able to use that. If B has a preimage, there exists a... okay, so Hx proves the if condition is true when the input is FA. Oh wait, but here's where we use the injectivity. To choose hex. Yeah, so this clearly, I see the injective use. Okay. The other side, what did the other side need to do? We assume that we have a left inverse. And we're implying that's injective. Okay, let's step through the proof. Okay, we intro it, then we obtain. So what is this obtain G, HG to find LE? That means that we're going to actually get the G, which is a function from B to A, and then we're going to get an HG, which says left inverse GF. Nice. Okay, then have G. Okay, this is going to duplicate. So now we have two terms of the exact same type. And then we're going to rewrite injective. Okay, that's kind of out of order, but that's okay. So here... Oh, no, wait, I skipped one. Rewrite left inverse at HG is going to then turn into for all x, gfx equals x. So that's at one of them. Then we're going to rewrite injective to be, fa1 equals fa2 implies a1 equals a2. And then here, this is kind of accessory. But, oh, those intros are nice. I really like those intros. We get the HF and the A1. Now, this thing doesn't really do anything except add a... I don't think I ever use it either. Let's get rid of that. So you have foo. And all we're trying to do here is kind of construct a term of type that satisfies kind of the left inverse property. And the only reason why we do this is because I wanted to practice applying HG to some element. Because we have this, so I just wanted to learn how to use that. And then we had to do symmetric. Okay, now we're here. Okay, so we got that. That was not really Actually, it did end up being useful because we rewrite HF there and we get A2. Then we rewrite HG there and we get A1 equals A2 and we can exact foo. Okay, I kind of don't like that proof. We're just going to keep doing it. If A1 not equal to A2. Oh no, wait. Alright, I'm not doing these other ones. I'll leave this stuff. I'm gonna delete this. All right, that was pretty fun. Let me see what the next exercises are. Prove that the inverse of a bijection is a bijection. Okay, so let's just try to write it down. Let's do okay, so first we say f of type A to B, and then now how did they define bijection? What? Oh, here we go. Bijective. Is this in function? Okay, this is in function. Injective and surjective. The thing is, injective. Wait, left inverse implies that it's oh, this is in MathLib. Oh, interesting. Is this using the Okay, cool. All right, good. You would hope so. But I guess yeah, left inverse implies injective, but injective doesn't imply left inverse unless it's non-empty. Yeah. It's kind of a interesting snafu. Um okay. Inverse, right inverse, set the left inverse. How do I just say how do I state? Let's just figure out how to state it. Because it doesn't seem like there's a specific in oh wait. Type class for inv so bijective inv f. Is that it? Doesn't seem right though. Because I think inv is working on This enables the notation or... No, this is some other stuff. This is not what I'm talking about. Yeah, you have to deconstruct it into a two-sided inverse. But left inverse implies... So wait, hold on. Do we have a theorem for... Because I might just do it... I might just do the MathLib proof as opposed to like do the whole thing. So we'll just say... exists a G from BA. We could just say... Yeah... Ay, ay, ay. Okay, case it with injectivity and subjectivity, and then we can oh, do we have to do the thing, man? If we instead got to assume that, because like we could also rewrite this, make it a little bit easier on us to do. Instead of just saying, we could say that I think we should be able to do left inverse GF, or let's say HL, and then HR right inverse G, do we have to do, let's see, hold on. Right inverse GF means that G is a right inverse to F. Yeah. And then how do we specify the inverse? We just need to say that there exists that that G is a bijection from, because these refer to the same G, I think. So this might be a simpler proof so that we don't have to exactly... And I believe that that's basically the same thing. Because now we can say, now we can easily derive, let's just say like have f-inj define be a term of type injective f by left inverse injective, and then can't I just do like this? Why didn't that work? I think I can also just do by exact HL. No? Why not? Oh, wait. No, but what's the theorem? It's called left inverse injective. Oh, but I have to provide... No, yeah, that's what I did. I think I need to do this. Exact... There we go. Okay. All right, so, and then... So this is kind of like similar. I forget the actual detail of it, but this is so boring. It's not math, man. All right, so just do the same thing. Okay, so now we have the kind of same thing. But I forget how it goes. It's like having a two-sided inverse means... Let me read the book again. How does the book go? Okay, let's just read this section again. It's not even that long. Oh, the multi-sets thing. Okay. The common thread we will follow for just about every structure introduced in this book will be to try to understand both the type of structures and the ways in which different instances of a given structure may interact. Sets interact with each other through functions. It is tempting to think of a function f from a set A to B in dynamic terms as a way to go from A to B. Similarly to the business with relations, it is straightforward to formalize this notion in ways that do not need to invoke any deep meaning of any given f. Everything that can be known about a function f is captured by its graph. Yeah, okay, that I know. Not all subsets correspond to functions, so we need a unique b for every a. The out degree of every whatever first in the bipartite graph. Okay, that is a function must send each element a to exactly one of b. Multi-valued functions are no good. All right, notation. The collection of all functions from a set A to set B is called BA. If we take seriously the notion that a function is really the same thing as its graph, we can view B pow A as a special subset of the power set of the Cartesian product. Wait, what does that even look like? Let's say that let's expand on that. The power set of the Cartesian product. We have like 1, 2, AB, 1A. There we go. Yes, this is exactly what I was going to do. A function with f of 1 equals A, f of 2 equals B. But the power set of A cross B is going to be every possible subset of this. Okay, that's, yeah. That's fine. That's all right. I'm okay with that. The wrong one. Every set A comes equipped with a special function called the identity, whose graph is diagonal in A cross A. More generally, the inclusion of any subset S of a set A determines a function S to A, setting every element of S to itself in A. If S is a subset of A, we denote f of S the subset of B. Okay, so it's just an implicit map. Okay, and they give a special name, then a restriction of S to B. From S to A is the inclusion. Okay, more notation. All right. Multi-sets, index sets. Yeah, let's skip this. We know this stuff. I just want to go to the part about the... If it's both injective and surjective, then it's bijective. But I want to see that part about the wait. So just to prove that the inverse of a bijection is a function is analogous to the fact that it's surjective. You don't actually need injectivity for this, I think. Which is 2.1? 2.1 defines a function how? Totality for all B and B exists in A. Okay, so totality is now single valuedness. For all B and B for all... Okay. I don't understand why it flipped it though. If F is surjective but not injective, there exists A1 and A2. Then in the flip graph, the same input is paired with two different outputs. That's not a function. Okay, that's right. Yes. You do need both of them. I was wrong. Okay. You definitely need both of them. Composition, second viewpoint. Okay. So let's say we have an injective and non-surjective function. Then so if G is a right inverse, that means that F after G, so we have 4 points here. So if F is surjective, then we're going to say that F has 4 points, G has 3 points, or A has 4, B has 3, and F has 4. Okay, we're going to say it's surjective. F after G equals identity on B. Then G is injective. If G is a left inverse of F, F is injective and G is surjective. And similarly, yeah. Left inverse GF implies injective. But did they say that? Is that in there? What is this proving? F is injective. Um. Uh. What is this one? Right inverse of injective of left inverse. Hold on. Let's try to figure out what this means. So we have A to B to A. A to B is the F. B to A is the G. This is injective. What's the syntax for injective? I actually really like that. Where did they have it? I'm pretty sure. Okay, these are the injections. So, and then F is injective. And then F is a left inverse of G, which means that F after G is equal to I on B, right? Okay. It's saying that if F is injective and F is the left inverse, then F is also a right inverse. So this together, F inj implies that if it's a right inverse, bro, I always forget this. Okay, so then what does it mean that if G after F equals the identity on A, So if G has a right inverse, it's surjective. So let's see if we can yeah, I want to prove that if we I want to prove the following. Before I do this, I want to say uh um uh that the G surge if left in. So what I'm saying is F is of type A to B. Okay, then what we're trying to prove is that we also assuming that left inverse G F. Okay, so now we want to prove that surjective G. Why did F not get Phailton for the binders? Why? What? What happened? Oh, you know why? Because I'm dumb. All right. Okay, so how do you prove that? So what do we know? We know that for all x, g of f of x is equal to x. We also know that f is injective. So let's just say have f inj type injective f defined by exact left inverse dot injective f gf by exact. What does this take? Oh, first you apply, wait, yeah, first you apply G and then you apply F. What's wrong with that? It takes a G and then an F. What did I do wrong? Is expected to have type left inverse. Wait, can I just provide it H? Okay. Well, that works. So now if I'm A and I'm sending stuff injectively, then uh I always think in terms of the size of the set. Like, for instance, we know that B is at least as big as A now because of the injectivity. Then if we want to recover all those points, from G or from B, Okay, so how am I going to prove it? I would say by contradiction, assume uh let's see, what are we trying to say? We're trying to show that G from B to A is surjective. So you assume that there's a B in B such that G of B is no. Assume there's an A in A such that there does not exist a B such that G of B is equal to A. So I don't know how I'm going to do this, but let's just say assume for contradiction that there is um an A in A such that there does not, oh, wait, you can't do that. How do you do does not exist? Exists, not exists. Oh, EXN. There we go. EXN a B, G of B. That's not G, not surge. Then refine FA. You don't need contradiction here. Um, that's it. FA, HA. What is HA? The Okay, yeah, that's just unraveling the definition. Then what? They say, hold on, in my notes, if you have an exist, exists, you use refine. But I don't get refine. Is there like a good video on like how to use refine? Oh, this is lean 3, right? I don't think that's what I want. They're improving. I think it's probably this. Tactics. Refine. No refine in here? What the hell? Bro, they get into writing your own macros, but they don't talk about refine? I think the problem is that chat might be giving me too complicated tactics. Like, I shouldn't even be using refine at this point. I think I just need to try to use rewrite. Okay, wait. All right, let's just get to the heart of what the hell refine does. And let's look at this here. So if I do refine FA, because I'm just like guessing at random. Refine is one of the most important make progress tactics in Lean because it lets you build the proof term you want even if you can't finish it yet. Think of it as refine T means I claim the goal can be solved I claim the goal can be solved by the term T. Please accept it and turn any missing parts into new goals. So what? Yeah, let's keep going. Lean goals are, I need a term of type G if your goal is G. And if you refine some expression, Lean tries to check that expression has type G. If it's missing pieces, it creates new goals for those pieces. Explicit hole, make a new goal here. Implicit hole, Lean, infer this. If you can't, it becomes a new goal. All right, refine for conjunctions. So what is and.intro? Here we go. Okay, wait, so no, this didn't do it. What? I don't know. Honestly, sometimes this IDE is like so janky. So what I'm trying to do is and.intro. But then why is this erroring? And.intro has type M2 to M3 to M2 to 3. But then this, didn't this say? Oh, because this whole thing. Okay, so wait. In this example, the and dot intro dot dot is the whole expression. The angle. See, the problem is there's so much syntax. It's like, okay, first off, we have this t, but then we have the t is an angle bracket. An angle bracket's something new altogether. The goal is a function type. You can build a lambda and leave the body as a new goal. So we take some A and then show how to construct a B. H, we have a function from A to B. And we're trying to create a... Wait, I don't get this one at all. Wouldn't you just exact H? After this, what do we have here? Oh, because the goal is no longer... But what if I just do this? Yeah, so, I mean, that's kind of... But it's like attempt to replace the current goal with this structure, this form. So, all right, so now... I don't get this at all, right? Like, they build an element of a type that is defined as a structure record with fields, including and, exist, prod, subject. What? Pack these pieces together. But like, where is the and in that? Like, why could that not be or? All right, I want to try this. If I do this, but I change this to or, or, invalid angled brackets notation. The expected type P or Q has more than one constructor. This notation can only be used when the expected type is an inductive type with a single constructor. Dude, I gotta get some food, man. This is getting to be a little bit much for me. But can't I just do this? Oh, because you never actually do this? That's okay, that's interesting. Example, construct a term of type nat cross bool by exact. Like what if I did this? Check. The expected type of this term could not be determined. Yeah, that's a very strange syntax. So it's clearly aware of the goal state because, well, we didn't check if this works, but it works. So example, my favorite pattern. Why is it talking to me like that? So to prove surjective for an arbitrary A, you must prove B and proof. Oh, but what is H? Okay, so FA is going to go here and this exists. So we're using, so for the exists, so in the surjective example, we are using FA of type B as a witness for the goal, the goal, the existential goal. But then what is H here? What if I do check HA? HA is a term of type G of f of A equals A. So I can apply. So this left inverse thing allows me to apply. Yeah, because if I unraveled it. So then I can just say HA. So that's it. So this is like one way of doing it. So we don't actually need this either. So to take A as any out of A, then use FA as the witness for the existential interjective. Then the definition of left inv gives a proof that this okay. All right, I think that's gonna be it. But that was actually really fun. I really did not like this proof. This confused the hell out of me, especially this thing. I did not like that. But all right, that's it. Some section 2. All right, peace.